Welcome to another episode of our educational podcast, where curiosity meets knowledge. If you're a student eager to explore the fascinating world of science and philosophy, you're in the right place. Join our community of learners and subscribe for free to access engaging content that enlightens and informs. Let's embark on a journey to understand how we can investigate our world using the powerful tool of the scientific method. Today, we're diving deep into how scientists turn questions into testable ideas and the steps they take to gather evidence and reach conclusions. The scientific method is a systematic process that scientists utilize to explore phenomena, make predictions, and draw conclusions. It starts with observation, which is identifying something in the natural world that piques curiosity. This might mean noticing that certain plants flourish in sunlight or that a specific area of the ocean appears to have an unusual number of dolphins. These initial observations then lead to questions, a crucial step that sets the stage for investigation. Consider Alexander Fleming, who made a groundbreaking discovery of penicillin. His journey started with keen observation. He noticed that mold had killed bacteria in a petri dish. This observation sparked a question that led to further research and discovery. Thus, the process begins with curiosity, attention to detail, and the courage to ask questions that challenge accepted beliefs. Following observation, the next step is forming a hypothesis. A hypothesis is a proposed explanation for observed phenomena, and it must fulfill several criteria. It should be testable, meaning you can gather data that may support or refute it. It must also be falsifiable, which is a key concept emphasized by the philosopher Karl Popper. He argued that the difference between science and non-science lies in the ability to make predictions that can be proven false through experimentation. For example, the statement "all swans are white" is easily testable because if someone finds a black swan, a hypothesis is disproven. In contrast, a hypothesis such as "there is an invisible dragon in my garage" is not falsifiable and therefore strays beyond scientific inquiry. Next, we move on to experiments, which are critical in evaluating hypotheses. Experiments should aim to isolate variables to determine whether the hypothesis holds true. A proper experiment includes a control group, which does not receive treatment, allowing scientists to compare against the experimental group, which does. A common example is drug trials. The control group receives a placebo, while the experimental group receives the actual medication. By comparing outcomes, researchers can conclude whether the treatment was effective. This systematic comparison ensures the reliability of results, making controlled experiments the gold standard for scientific testing. However, not all fields allow for controlled experimentation. In areas like astronomy and ecology, where manipulation of variables may be impractical, scientists often rely on observational studies instead. Once the experiments have been conducted, the collection and analysis of data come next. Data can be broadly classified as either quantitative, which includes numerical data, or qualitative, which encompasses descriptive data. Analyzing this data involves interpreting results to determine if they support the initial hypothesis. This is where statistics play a vital role. Statistical tools help scientists understand whether the results they observed were significant or merely a product of chance. By using graphs, charts, and models, scientists can visualize data effectively and identify underlying patterns. It's crucial to approach data analysis with a sense of objectivity. The interpretation of data can be clouded by biases, which is why statistical methods are employed to minimize subjectivity. Possessing the skill to gather and analyze data is fundamental for any scientist. After analyzing the data, scientists reach a stage in which they draw conclusions from their findings. This involves deciding if the data supports the hypothesis. If the evidence backs it up, the hypothesis might get refined and put through additional testing. If not, it may be rejected or altered based on the findings. A vital point to understand is that in science, hypotheses are not ever proven definitively true. Instead, they are supported by evidence, which is essential for scientific inquiry's self-correcting nature. Scientific knowledge remains provisional, it is always ready to be adjusted when new evidence emerges. This applies even to well-accepted theories like evolution or gravity. They could be revised if new data contradicts them. Drawing conclusions also includes communicating findings, a crucial aspect of the scientific process. This allows others in the scientific community to review, replicate, and expand upon these findings, underscoring the importance of peer review in scientific research. Speaking of peer review, reproducibility is another core principle underpinning the scientific method. A scientific finding must be reproducible by different scientists using the same methods. If a result cannot be independently reproduced, it becomes questionable. Peer review serves as a mechanism to ensure research is robust, ethical, and well-designed. It prevents flawed or fraudulent studies from being published. Recently, the scientific community has faced a reproducibility crisis. Many studies have proven difficult or impossible to replicate. This has highlighted the need for transparency in research methods and stronger quality assurance measures. Additionally, the scientific method employs both inductive and deductive reasoning. Inductive reasoning develops general theories from specific observations, while deductive reasoning applies general theories to make specific predictions. The method, often described as hypothetico-deductive, illustrates this cycle clearly, forming hypotheses through induction, then utilizing deduction to test these predictions through experimentation. For instance, if a scientist observes that specific plants grow better with increased sunlight, they hypothesize that more sunlight promotes plant growth and then create a specific prediction to test this. Through this back and forth of hypothesis formation and testing, scientific inquiry advances. However, it's essential to recognize the limits of the scientific method. It can only investigate questions that can be empirically tested. Science cannot provide answers to questions about values or meanings. For example, while science can instruct on how to create a bomb, it cannot impart whether it is morally right to use one. Therefore, understanding the boundaries of what science can address is crucial to avoid scientism, the misunderstanding that only science can yield knowledge. Science remains a powerful tool, but it is just one approach among many to understand complex aspects of our lives. Overall, the scientific method stands as one of humanity's remarkable achievements. It has profoundly reshaped our understanding of the universe, yielding countless advances in technology and improving life for billions. Beyond simply belonging to scientists, the method represents a way of thinking that everyone can incorporate into their lives. By fostering a mindset of observation, questioning, testing, and analyzing, we can all enhance our decision-making skills and tackle challenges more effectively. The scientific method not only embodies values of curiosity and skepticism but is also a commitment to drawing knowledge from evidence. Today, we explored the scientific method, a cornerstone of scientific inquiry that guides how we investigate phenomena and form conclusions. We began by discussing observation as the catalyst for questioning, followed by formulating and testing hypotheses through structured experiments. From analyzing data and drawing conclusions to understanding the significance of reproducibility and peer review, each step is vital to fostering reliable knowledge. We recognized the scientific method's limitations while honoring its power in transforming our understanding of the world around us. This structured approach allows not only scientists but each of us to engage thoughtfully with our environment and the complexities of our existence. Thank you for joining us in this episode on the scientific method. We hope you are inspired to apply this systematic approach to your own learning and exploration. Remember, curiosity and skepticism are your allies in the quest for knowledge. If you found today's discussion valuable, please subscribe for more insightful content that fuels your curiosity and understanding. Until next time, keep wondering and keep questioning. The world has so much to teach you.